For centuries, philosophers suggested that everything around us might carry some form of awareness. Now in 2025, science is beginning to collect data that gives this old idea fresh weight. The thought remains controversial, and throughout this video, we will separate measurements that can be confirmed from interpretations that are still speculative. Researchers now see striking overlaps. The human brain and the universe each contain on the order of 100 billion organized nodes. Both follow similar connectivity laws, and both evolve across time. To ground this in evidence, we will later look at the newly completed mouse brain wiring map that stunned neuroscientists and a high-definition cosmic filament image captured with the Muse instrument. Some scientists suggest these resemblances could mean consciousness is woven into reality itself, while others remain deeply skeptical. Could your life be just one node in a much wider system of information? We will examine both the supporting evidence and the unresolved questions, starting with a surprising numerical match. The brain and the universe, same numbers, different scales. When researchers first compared the brain to the universe, it wasn't the fine details that caught their attention but the numbers themselves. Inside the human skull, neurons form dense networks numbering in the tens of billions. Across the observable cosmos, galaxies cluster into filaments that, surprisingly, also fall on the order of 100 billion. The measured scale is very different. The brain occupies centimeters. The cosmic web stretches tens of billions of light years. Yet both systems converge on the same order of magnitude for their primary building blocks. By 2025, newer datasets added strength to these comparisons. Neuroscientists advanced large-scale connectome mapping, while astrophysicists released deeper galaxy surveys and more realistic simulations. Together, the datasets validated that the Neuron galaxy match is not exact in count, but does consistently remain on the scale of 10-11 nodes. The similarity becomes more striking once we carry the comparison past raw counts to include the way these nodes link together. Neurons communicate through electrochemical signals, strengthening or weakening connections based on activity across countless synapses. Galaxies, meanwhile, connect through gravity, tracing filaments of dark matter and gas that channel matter through space over cosmic time. The MyCRON's Consortium's 2025 release illustrates how far the brain side of this effort has progressed. Their mapped volume of mouse visual cortex included around 75,000,084,000 neurons tied together by nearly 500 million synapses, all within a piece of tissue smaller than a poppy seed. On the astronomy side, next-generation observations provided a complementary advance. Deep Muse spectroscopy yielded a 3 million light-year-long filament image in unprecedented detail, while updated cosmological simulations generated higher-resolution views of matter clustering. These projects offered genuine case studies for comparing biological and cosmic networks with far more confidence than before. The question that emerges is not whether galaxies and neurons physically interact. They obviously do not. But why two such distinct systems end up looking mathematically alike? One is a warm, soft structure of cells and chemicals, the other a vast distribution of matter shaped by gravity. Their governing laws differ completely in mechanism, yet both stabilize into complex webs of comparable statistical density, each hovering around 100 billion nodes. This raises the possibility that constraints on efficiency and stability, information distribution in the brain, matter flow through filaments, naturally push systems towards similar network scales. Physicist Franco Vazza and neurosurgeon Alberto Felletti first formalized this comparison a few years ago, running statistical tests on both architectures, and their results remain a grounding point. Despite being separated by about 27 orders of magnitude, the two networks share the same morphology and clustering patterns when analyzed by spectrum and connectivity. The 2025 refinements push these analyses further. Layered imaging methods clarified how clusters in brain tissue form and reorganize over time, solidifying neuron number ranges rather than producing radical revisions. In astronomy, updated surveys corrected for hidden galaxies and observational limits, narrowing estimates but still confirming that galaxy counts fall within the same magnitude as neuronal counts. At this level, it becomes less about exact agreement and more about robust categories. Both systems build webs composed of tens to hundreds of billions of nodes, and both show connectivity that follows comparable scaling laws. That kind of match goes beyond visual coincidence and into quantifiable territory. This equivalence in order of node count naturally leads to thought experiments. Imagine zooming outward from a single neuron. Its fine filaments branch and interlace, becoming part of a living circuit that processes information. Now step outward not by millimeters but by light years, and galaxies too inhabit filaments, clustering where strands intersect. The statistics charted in 2025 reinforce this impression by providing direct comparisons of connectivity distributions. Researchers consistently see overlapping patterns across the frequency spectrum, suggesting that the same principles may organize matter and information regardless of substrate. At the same time, several scientists urge caution. Visual similarity and shared statistics must not be mistaken for identical function. A network of galaxies is not processing thoughts, just as a brain is not pulling in surrounding star systems. Even with those caveats, the resonance is difficult to dismiss. Both systems are more than the sum of their parts precisely because of how their nodes connect. Stripped of surrounding tissue, a neuron carries little meaning. Isolated in space, a galaxy does not trace a web. But when measured as networks, similarities appeared across domains. Researchers emphasize that this is not a mystical observation but one rooted in data collection and analysis. The MyCR-ON's team's microscopic mapping and Muse's macroscopic filament imaging are not metaphors but carefully constructed records, each revealing organizational patterns that statistical frameworks like those used by Vaza and Feletti can legitimately compare. This has important implications. The brain cannot be reduced to a pile of disconnected cells, just as the universe is not randomly arranged bodies adrift in emptiness. Both exist instead as organized complexes of nodes and linkages that pass signals or matter at multiple scales. Their apparent convergence on the order of 10-11 nodes might reflect deeper principles about how complexity stabilizes. Researchers debate whether this is simply a statistical inevitability of network science, or whether it points towards some unifying mathematical architecture underpinning different realms of reality. However interpreted, the growing dataset narrows speculation by forcing it to confront evidence. Electron microscopy, optical and radio surveys, machine learning reconstructions, these are hard tools producing real numbers. When results from different domains independently confirm node counts on the same magnitude, separated by physically impossible distances in scale, curiosity about why this happens cannot be easily waved away. A neuron is not a galaxy, but the fact that their networks echo in both number and form means something about structure and constraint is at play. And so the brain and the universe become two case studies of nature building complexity. They differ in function and energy, but converge in morphology and statistics. Each forms a mesh that sustains activity beyond what its elemental parts suggest. The brain channels thought across its circuits. The cosmic web channels matter between clusters. It is in these parallels that the discussion begins to push beyond coincidence. From there, the comparison becomes less about raw counts and more about patterns repeated at both scales. When we place high-resolution brain images next to maps of galactic filaments, the resemblance strikes us immediately. What once seemed a surface similarity is now backed by measurable spectra and consistent mathematical relationships. And it leads directly into the next consideration: why the branching architectures themselves look the same, and what scientific explanations could account for that persistence across two vastly different environments. Patterns that repeat across space and mind. When scientists turned their attention to repeating forms across biology and cosmology, they were not looking for vague resemblances but testable patterns. At first glance, the branching of neurons in the brain and the filaments of galaxies across the universe do look alike, but the real interest comes from measuring whether these systems share the same statistical behavior. In recent years, researchers such as Franco Vazza and Alberto Felletti carried this comparison further, treating both the brain and the cosmic web as networks that can be analyzed with identical tools. The critical shift in 2025 was moving away from the casual observation that both look like webs toward using power spectrum analysis and network metrics. This approach quantifies how structures repeat at different scales, producing curves that summarize connectivity, clustering, and distribution. For the brain, datasets came from increasingly fine-grained cortical maps that trace neuronal wiring in 3 dimensions. For the universe, astronomers relied on high-resolution surveys and simulations of large-scale structure. When these curves were compared side by side, both systems displayed remarkably similar slopes in their power spectra and echoed one another in network measurements such as clustering coefficients and degree distributions. What this means is that both networks distribute complexity in the same statistical way. Neurons cluster into microcircuits, which then link into larger cortical assemblies. Galaxies aggregate into groups, which themselves belong to superclusters interconnected by filaments. The mathematics that describes this layering follows nearly identical rules, despite the systems being separated by almost 30 orders of magnitude in scale. Importantly, the similarity does not show that the universe thinks like a brain, but it does demonstrate that both rely on the same scaling law. This excludes the argument that the likeness is coincidental surface imagery. It is not about appearance. It is about mathematics recurring in 2 very different physical domains. Later in this video, we will place those spectral curves side by side to show visually what this numerical alignment looks like and what it does not imply. For a long time, many scientists dismissed the resemblance as accidental. After all, biological growth follows chemical signaling and genetic coding, while cosmic evolution comes from gravitational pull and expanding spacetime. But once statistical signatures started to align, the dismissal grew less convincing. Power spectrum results reveal how roughness or clustering emerges across multiple scales. If neurons and galaxies both scale in the same way, then shared principles are shaping otherwise unrelated processes. It helps to think in terms of efficiency. In the brain, neurons need to transmit signals widely without expending too much metabolic energy. In the universe, galaxies need to gather material and redistribute it without destabilizing large regions. When any system tries to maximize communication while minimizing resource use, certain network forms naturally arise. That principle is known in many fields as small world efficiency, and both the cerebral cortex and the cosmic web appear to converge on it. Power spectra and network statistics now show that this is not just a striking metaphor, it is a repeatable outcome across scales. To illustrate the point further, imagine 2 unrelated languages developed independently in isolated regions. At a glance, their alphabets look different, yet when linguists measure frequency distributions of words, sentence lengths, and grammar patterns, both languages align in ways that suggest shared constraints. No one would conclude that the languages are communicating the same message, only that the rules governing efficient communication pull them in similar directions. Something like that seems to be happening between neural tissue and cosmic structure, separate processes producing results guided by comparable mathematical pressures. Computational methods have strengthened these insights. Neuroscientists used supercomputers to catalog the intricate web of cortical neurons, producing massive data blocks that could be re-rendered into spectral diagrams. At the same time, astrophysicists advance simulations that recreate cosmic evolution under the laws of physics, also producing spectral diagrams. When the two sets of data were placed alongside one another, the slopes of their power spectra lined up in a way that exceeded expectation. This is the heart of the Vasa and Felitti work, and the reason their findings attract attention. The brain and the universe appear to fall under the same category of network geometry. This conclusion does not mean the systems perform equivalent functions. A neuron has signaling roles, while a galaxy has gravitational ones. The important finding is that both avoid randomness or unlimited branching. Instead, they stabilize into networks optimized for balance between connectivity and cost. Though they do not think the same way, they organize statistically under a comparable rule set. Recognizing this subtlety keeps the fascination alive while avoiding overstatement. The implications are broad. If both systems obey the same scaling code, then constraints on complexity may apply universally. Not only might galaxies and neurons share this law, but any large network, biological, physical, or even digital, could converge toward it. Some computer scientists suspect engineered networks like artificial intelligence systems may fall into the same category. If true, it would mean that different domains of reality, from microscopic brains to cosmic filaments, embody a common mathematical architecture simply because it is the most efficient option nature allows. Such findings change how scientists understand the word coincidence. A glance at clouds forming an animal shape is coincidence because statistical checks will not confirm a repeated rule. But here, statistical checks do confirm repeated rules. The power spectrum curves do not depend on subjective impressions. They quantify the degree of clustering at every scale. When different systems produce the same quantified curve, coincidence becomes less likely. Instead, the pattern points toward deep constraints on how complexity organizes. In concrete terms, both the cerebral cortex and the cosmic web appear to access similar efficiencies. They use modest inputs, metabolic resources in the brain, gravitational interactions in space, to sustain immense connectivity without redundancy. The power spectra show this efficiency in statistical form, making it more than speculation. As a result, scientists no longer separate the two pictures into chance likeness versus real process. They treat them as separate domains manifesting a shared scaling principle. Seen this way, the network suggests that information, not just matter, helps define organization. In the brain, that information flows as electrical signaling. In the universe, it flows as gravitational potentials shaping matter distribution. The functions differ, but the information architecture looks mathematically equivalent. For scientists, this opens the possibility that organizational laws extend well beyond what biology or cosmology alone can explain. Yet questions remain. If such laws govern both neurons and galaxies, where else do they apply? Some researchers ask whether similar spectra would emerge in protein interaction networks, ecological webs, or economic systems. The issue is not about consciousness itself, but about how natural structures self-organize under universal constraints. Measuring repeated laws pushes exploration outward, but it also raises the deeper puzzle of why such laws exist in the first place. That deeper puzzle brings us back to consciousness itself. If the brain's architecture echoes cosmic architecture, but functionally they remain distinct, then explaining how awareness arises requires a different angle of inquiry. Matter alone does not fully account for why thoughts exist inside neural tissue. To approach that question, scientists have begun probing even smaller scales, looking for processes that might bridge physics and experience. They have focused not on networks at the largest scale, but on interactions at the smallest, where quantum effects may play a decisive role. The quantum secret, consciousness in the smallest scales. At the smallest scales, researchers are now shifting attention to quantum processes as possible contributors to consciousness. This line of investigation has gained momentum not because it has delivered firm answers, but because classical neuroscience continues to leave a critical gap. Scientists can record neuron firing, track circuit activity, and map neural wiring in extraordinary detail. Yet none of these measurements reveal how subjective experience arises. For some, the limits of purely classical explanations justify looking at quantum mechanics as a possible additional layer that could shape awareness. Others remain unconvinced, warning that the brain is too warm and noisy to sustain delicate quantum effects. This question lies at the center of what philosopher David Chalmers termed the hard problem of consciousness. Describing neural activity is not the same as explaining why activity comes with an inner feel. From a physical standpoint, stacking atoms together should only result in ever more sophisticated machines. Yet human brains produce thoughts, sensations, and self-awareness. To some, this suggests missing ingredients in our models of mind. It is in this gap that quantum theories of consciousness have positioned themselves, not as proof, but as testable alternatives to purely classical accounts. Emerging evidence in 2025 does not resolve the argument, but does show that quantum biology might be more resilient than once believed. For decades, physicists assumed quantum coherence, where states exist in delicate superpositions, would collapse instantly in warm biological environments. Surprisingly, experiments in photosynthesis and bird navigation demonstrated that quantum effects can persist inside living systems long enough to play a functional role. These precedents opened the door for speculation that similar processes could exist in neurons, perhaps influencing how information is combined into unified experience. Several concrete research programs now experiment with ways to test this. One historically prominent proposal is the Orchor model developed by Roger Penrose and Stuart Hameroff in the 1990s. They suggested that tiny structures inside neurons, called microtubules, might sustain quantum states long enough to affect consciousness. Mainstream scientists criticized the idea heavily, pointing out that thermal noise should overwhelm such coherence. Even today, the Orchor hypothesis remains controversial, yet its persistence as a research question underscores how unresolved the issue is. While not accepted as established science, it frames a starting point for designing experiments that probe whether quantum events scale up into awareness. More recently, neuroscientist Christoph Koch collaborated with researchers at Google Quantum AI, exploring whether entangled qubits could one day be used to test how brain signals might interact with quantum states. In an interview, Koch made clear he was open to the idea that quantum mechanics contributes to consciousness, but also skeptical, emphasizing how technically difficult it would be to detect such faint effects in the noisy background of biological tissue. He proposed designing experiments that would measure whether neural systems can induce or interact with entanglement, though he acknowledged these remain ambitious projects for the future rather than present-day results. Another experimental clue comes from anesthesiology. Several teams studying xenon, a noble gas used as an anesthetic, have found differences in effectiveness between isotopes of xenon. These variations are difficult to explain using purely classical chemistry, leading some to suggest that subtle nuclear or quantum properties might help suppress consciousness. While the findings are preliminary and hotly debated, they provide a rare case where consciousness, medical practice, and quantum physics intersect. Researchers continue to refine these experiments in hopes of confirming whether genuine quantum processes are at play. Despite this growing body of work, critics remain cautious. Physicist Max Tegmark and others have argued for years that maintaining useful quantum states in neurons is implausible, as decoherence should occur almost instantly. Many neuroscientists agree and view consciousness as an emergent property of classical information integration rather than quantum processing. Between advocates proposing bold mechanisms and skeptics demanding firmer evidence, the debate stays alive but unresolved. Still, intriguing parallels keep researchers at the table. Quantum biology has already changed how scientists view photosynthesis. Energy transfer within plant cells uses interference effects to maximize efficiency. Birds appear able to sense Earth's magnetic field through entangled radical pairs in their retinas. These examples prove that life does sometimes leverage quantum states even under noisy conditions. The open question is whether neurons, or perhaps brain microtubules, do anything similar, and if they do, whether this helps explain subjective experience. Supporters of quantum consciousness models often describe the brain as more than a machine built from matter alone. If quantum coherence persists even fleetingly in neuronal structures, it could act as an organizing principle, amplifying fragile states into meaningful patterns. This perspective suggests that awareness might not spring from complexity alone, but from matter's access to quantum-level possibilities. The brain, then, could be seen as a system that both stabilizes and interprets these subtle signals, transforming them into lived realities. At the same time, a sober view requires recognizing limits. No quantum consciousness theory has yet delivered definitive proof. Experiments remain indirect and interpretations contested. Even proponents acknowledge that extraordinary claims demand extraordinary evidence, and the tests needed to demonstrate a quantum basis for consciousness are technically daunting. Building tools capable of measuring entanglement or coherence inside cells is a frontier task, one that may take decades to resolve. Nevertheless, the discussion has gained legitimacy. Where once these ideas were treated purely as metaphysical speculation, physics and neuroscience journals now publish exploratory results and proposals. Collaborations between experimentalists and theorists signal that the subject has crossed a threshold. No longer dismissed outright, it is now regarded as a topic to investigate carefully, with the understanding that most initial hypotheses may fail. In other words, speculation is being transformed into conjecture that can be probed, refined, or rejected by data. Philosophically, this shift invites a reinterpretation of consciousness. If quantum processes do turn out to play a role, awareness may not appear suddenly at some threshold of neuronal complexity. Instead, it could emerge from rules already present in the fabric of reality, with brains acting as amplifiers of these fundamental structures. In this view, consciousness would resemble a background potential waiting to be expressed, rather than a mysterious side effect of biological evolution. Such a model does not imply every object has a mind, but it does suggest that the universe may be more saturated with proto-conscious potential than previously thought. For audiences following this conversation, it is important to keep two threads in balance. On one side is the clear skepticism. Most neuroscientists continue to treat classical explanations as sufficient until quantum evidence is strong. On the other side is the growing sense that conventional methods alone have failed to resolve the hard problem. The possibility that quantum physics contributes to consciousness remains open, though unproven, and it raises questions that cut across neuroscience, physics, and philosophy alike. As investigations continue, the debate is expanding beyond laboratory data to cultural and philosophical discussions about the nature of reality. What if consciousness is not a late-stage accident of evolution, but connected to structures embedded in matter itself? This question leads naturally to a framework that takes seriously the idea that mind-like qualities might operate at many different levels of existence. With that broader perspective, long-standing philosophical ideas about the mental dimension of reality are returning to modern scientific debate in surprising ways. Panpsychism moves into mainstream debate. The persistence of unanswered questions about consciousness has created room for older ideas to return with renewed relevance. Among them is panpsychism, the view that consciousness, in some form, may be a fundamental and pervasive property of reality. Once confined to philosophy, panpsychism has now entered more mainstream scientific conversations. Not as established science, and not as consensus, but increasingly as a philosophical hypothesis that some researchers consider worth testing against emerging data. This view has a long history. Ancient thinkers from Greece to early modern Europe speculated that matter might carry mind-like qualities. By the Enlightenment, however, natural science moved toward explanations based solely on mechanisms, chemistry, and physical laws. As experimental physics and biology advanced, panpsychism was pushed aside. For centuries, it survived only in philosophical debates, dismissed by most scientists as either mystical or regressive. The narrative was simple. Matter was unconscious, inert, and law-bound, while conscious minds emerged only through the exceptional complexity of brains. That model dominated natural science through the modern period, and it left panpsychism to the margins. But in the 20th and 21st centuries, neuroscience and physics kept running into the same problem. The brain could be mapped in detail, its neurons charted and its circuits analyzed, but the step where electrical signals produce subjective experience remained unexplained. This gap is what philosophers like David Chalmers called the hard problem. As dissatisfaction grew, panpsychism resurfaced, not to restore animism or mysticism, but to offer an alternative hypothesis. Maybe mind is not generated by matter at a threshold of complexity, but is instead present in the fundamental ingredients of nature. This does not mean a stone thinks like a human being, but that matter may already contain proto-conscious qualities that, in complex systems like brains, amplify into the rich awareness we actually know. Philosophers such as Philip Goff have been particularly influential in reframing this thought. In recent books and papers, Goff presents panpsychism as the most straightforward way to bridge the hard problem. If subjective consciousness cannot be reduced to physical processes alone, then it may be that physical reality already contains consciousness at its core. His arguments are philosophical, but they connect with a growing scientific culture looking for options beyond strict materialism. By 2025, his ideas are not fringe conversation pieces, but discussion points at interdisciplinary conferences where neuroscientists, physicists, and philosophers meet to explore what can and cannot be ruled out. Part of this renewed traction comes from advances in other areas. Quantum biology revealed that coherence survives longer in living systems than earlier models allowed. Cosmic and neural network studies suggested strikingly parallel architectures. Neuroscience showed what classical reductionism could explain, but also where it stalled. Together, these fields supplied new contexts in which panpsychism looks less like mysticism and more like a conceptual framework that might guide empirical questions. Researchers do not claim proof, but they increasingly view it as a hypothesis that can be formalized and tested indirectly by searching for consistent signatures across physics and biology. To maintain accuracy, it's important to stress the nuance here. Panpsychism has not become a dominant position. Most scientists remain skeptical. For many, it is less a conviction and more a placeholder, an option worth entertaining because conventional approaches to consciousness continue to fall short. Critics point out that until panpsychism makes specific, verifiable predictions, it remains philosophy, not science. Supporters counter that the history of research often begins with frameworks that only later become testable. Either way, the debate itself marks progress. Panpsychism is no longer pushed aside without discussion, but considered seriously as one among several conceptual alternatives. This change is visible in research settings. At neuroscience conferences in 2024 and 2025, panels explored how panpsychism compares to theories like integrated information theory and global workspace models. Papers have appeared in interdisciplinary journals evaluating whether universal consciousness hypotheses align with current physics or whether they strain consistency. These are not declarations of truth, but attempts to frame measurable questions. If all matter shares mind-like qualities, how might signature patterns manifest at the neuronal or quantum level? What sorts of experiments could confirm or disconfirm such claims? By focusing on testability, proponents reposition panpsychism alongside other models rather than apart from them. The philosophical boundaries are also clearer now than they were centuries ago. Panpsychism does not claim that every particle harbors thoughts or intentions. Instead, it suggests that the raw material of consciousness, however minimal, is embedded within physical reality. Just as charge or mass are seen as universal attributes, proto-consciousness might also be fundamental. More complex systems, like nervous tissue, would then integrate and magnify this property into the kinds of awareness we recognize. The principle aligns with how information behaves at different scales, distributed at the micro level, but coherent and expressive at the macro level. The appeal of this continuum model is that it explains why conscious experience feels irreducible. If awareness already threads through existence in basic form, then brains do not create it out of nothing. They elaborate and organize what is already available. This has cultural as well as scientific impact. Where ordinary audiences once associated panpsychism with mysticism, they now encounter it in lectures alongside other theories of mind, treated not as folklore but as one possible framework among many. Philosophers, neuroscientists, and physicists find it a shared language for discussing basic puzzles where traditional science alone has stalled. Yet resistance remains strong. Many scientists worry that talk of proto-minds risks blurring the boundary between empiricism and metaphysics. They insist that the correct path is to continue refining neuroscientific models until a better theory emerges from measurable results, not to reach back to speculative philosophy. They argue panpsychism may distract from productive inquiry. Still, even critics recognize that its return to conference panels, journals, and classrooms signals deep concern about the limits of reductionism and pressure to consider alternatives, even if provisionally. This shift matters. It reshapes how the hard problem is approached in research culture. Instead of calling panpsychism mystical, mainstream discussions now ask whether any empirical avenues can incorporate it. This does not mean consensus endorsement. It means willingness to test. Interdisciplinary teams pursue projects inspired partly by these questions, studying how matter organizes through network science, or how quantum properties influence biology, without dismissing the idea outright. Panpsychism is thus moving from a forbidden word in scientific dialogue toward a potential, if controversial, framework. The significance reaches beyond philosophy into practical science. If consciousness is a gradient property, then measuring degrees of it across systems might become possible. This is why some researchers explore parallels between connectivity in brains and galaxies, or between coherence in cells and coherence in quantum systems. For panpsychism, the aim is not to prove that stones have minds, but to explore whether universal laws of organization reflect ways in which matter participates in awareness. Even partial success in testing such questions would reshape how science defines the boundaries of mind. What stands out most in 2025 is that the debate has crossed a threshold. Panpsychism is present in academic discussions where it would have been excluded a century ago. It stands beside other models of consciousness as an option under review. It is still speculative, often criticized, and lacking decisive experimental support. But the fact that reputable researchers assess its ideas in light of neuroscience, physics, and philosophy means that curiosity now outweighs dismissal. For a subject long excluded from mainstream science, this is a fundamental change. That change, in turn, is reshaping how scientists expect future tools to perform. As empirical methods sharpen, discussions about panpsychism begin to intersect with the very technologies that probe the architecture of the brain itself. If awareness is indeed tied to organization at deep levels of matter, then studying how neurons connect, oscillate, and transmit signals may reveal patterns that speak directly to the hypothesis. And so the stage is set for a closer look at the structures within the brain, structures that could show whether hidden architectures align with the organizing principles panpsychism points toward. New brain mapping tech unveils hidden architecture. For years, neuroscientists assumed brain mapping had already captured the essential picture. Neurons could be traced, their firing patterns tracked, and wiring diagrams assembled. Large projects cataloged billions of neural connections into structured maps, and from the outside, the field seemed almost complete. Yet by 2025, that impression had dramatically changed. New technologies revealed that earlier maps presented only the surface layer. Underneath the familiar diagrams of neurons and synapses lay hidden networks, dense with activity and interaction, that older tools could not resolve. What once seemed like a nearly finished atlas of the brain turned into the opening chapter of a far more complex story. Traditional imaging produced what might be compared to subway schematics, clear lines between fixed stops, representing neurons and their synaptic partners. These diagrams established the brain's structural backbone, but left out much of the activity flowing through it. Electrical oscillations, chemical gradients, and network scale rhythms were dismissed as noise or averaged out by instruments too slow or coarse for fine detail. The resulting maps implied a rigid system of predefined pathways, but reality was more dynamic. By overlooking how activity surges, ripples, and reorganizes in real time, early surveys missed much of what the brain actually does. The breakthrough came with instrumentation capable of capturing structure and dynamics together. In April 2025, the MyCRONS consortium published the most comprehensive connectome yet, a cubic millimeter of mouse visual cortex reconstructed at nanometer resolution. Within that tiny piece of tissue, researchers identified roughly 75,000,084,000 neurons and nearly 500 million synapses. Every axon, dendrite, and synaptic contact was precisely charted. This level of mapping was far beyond anything available before, offering not just a wiring diagram but an unprecedented opportunity to study how connectivity shapes computation. As project leader Sebastian Seung emphasized, a connectome is not the same as code. It does not solve the mystery of consciousness outright, but it provides the raw framework against which hypotheses about neural function can now be tested in depth. Equally significant was the shift toward capturing the brain as a living, fluctuating system. The new mapping tools do not only mark which neurons connect, but also record the direction, timing, and oscillatory pulses traveling through those links. With higher resolution, previously invisible wave-like fields became measurable. Local bursts of gamma activity aligned with broader slow oscillations, and coordinated patterns extended across cortical regions that appeared separate in static imaging. Instead of static cabling, the brain began to appear as a landscape of flows. This interpretation gained experimental support from parallel efforts with brain organoids. In 2025, researchers reported using ultra-high-density CMOS microelectrode arrays, devices containing tens of thousands of sensors, to capture activity at single-cell precision across entire organoids. These arrays detected how signals moved through tissue, their frequencies, and how velocity of propagation shifted under drug interventions. For the first time, it was possible to see how specific rhythms, delta, theta, gamma bands, spread through a network, forming spatial patterns across hundreds of thousands of neurons. The findings offered new readouts of hidden architecture, not additional wiring, but dynamic signatures shaping how activity integrated across the whole system. When combined, these advances create a dual picture. The MyCRONS maps expose the physical foundation of one cortical block, while CMOS recordings reveal its waves and harmonics in action. Neurons are not only structural nodes, but participants in oscillations that broadcast across distances, syncing ensembles into unified activity. Awareness, in this framework, may not arise from isolated spikes, but from the interplay of rhythms sprawled across many regions. Observing this interplay does not explain the hard problem directly, but it gives scientists tools to test how structure and dynamics cooperate to generate integrated states. Researchers highlight the coherence that emerges from these oscillations. Much like harmonics in sound, brain rhythms stack and shift, allowing countless neurons to operate in coordination. Gamma waves may group signals into packets lasting milliseconds, while slower oscillations set broader temporal contexts. Depending on state, wakefulness, sleep, focused attention, different rhythms dominate or align, reorganizing which regions synchronize and when. Only with instruments capable of resolving both microsecond timing and large-scale propagation can this shifting landscape be visualized. The organoid recordings confirmed how such rhythms change under pharmacological influence, providing a new bridge between experimental neuroscience and therapies for disorders linked to disrupted synchronization. The implications extend well beyond metaphor. Older connectome maps presented neurons as elements of a machine. The new imaging reveals collective behavior better described as fields. These are not poetic abstractions. They are measurable propagation signatures, registered across thousands of sensors, that show signals traveling with specific velocities and forming repeatable spatial patterns. In one experiment, cortical organoids exhibited bands of activity that organized themselves differently depending on external conditions, suggesting the architecture of brain function is inseparable from the real-time field dynamics expressed through its networks. Such observations also connect back to long-standing theories about integrated brain activity. Proposals like global workspace theory and integrated information theory argue that consciousness may depend on large-scale coordination distributed across nodes. High-density mapping now provides a possible substrate for testing those views directly. With the 2025 reconstructions, researchers can see both the static scaffolding and the oscillatory waves passing through it, allowing detailed models of how structures enable fluid, shifting modes of information integration. The work also shifts clinical horizons. Structural brain imaging has long been central in diagnosing damage from injury or disease. The ability to chart oscillatory disruption at fine scales could expand those capabilities. Disorders such as epilepsy, schizophrenia, or Alzheimer's involve not only anatomical degeneration, but altered rhythms at network levels. By mapping coherence and propagation within organoids and cortical tissue, researchers hope to identify biomarkers of pathology invisible to standard imaging. Instead of seeing illness solely as broken wiring, clinicians may increasingly interpret it as shifts in dynamic harmony. Treatments might therefore aim less at repairing structures than at restoring healthy patterns of flow. Taken together, these findings revise what a brain map means. A century of neuroscience treated neurons and synapses as the units of analysis, building increasingly detailed connection charts. The technologies now in active use indicate that this is only half the picture. Equally critical are the patterns of oscillation threading through those connections, producing fields that expand and contract over time. With access to those dynamics, researchers no longer see the brain as a nearly static mechanism, but as a system that continuously reshapes itself through coordination across scales. Importantly, these results are not presented as final answers to how consciousness originates. The MyCR-ONS project itself emphasizes that maps, even at nanometer resolution, will not explain awareness. Instead, they establish the ground on which serious explanations can be tested. As Hume phrased it, structure frames function, but structure is not function itself. The hidden architectures now visible do not solve the hard problem, but they change how neuroscience frames it, away from speculation without data and toward hypotheses constrained by measurable organization. The broader significance is that the brain now appears to operate under principles familiar elsewhere in science. Its oscillatory fields recall resonances seen in physical systems, while its networking efficiency resembles solutions observed in other complex networks. Neurons fire individually, yet their effects travel as waves tied to underlying geometry. The image that remains is not a computer-like diagram but a dynamic field, continuous and collective. As a result, the conversation about hidden architectures moves beyond description of one organ and into comparisons with other systems shaped by flow, scale, and distributed coherence. The brain's new maps invite questions about whether similar organizational principles operate at orders of magnitude greater than millimeters and milliseconds. If neural structures form dynamic webs that carry information through harmonized fields, then it is natural to wonder where else nature uses this same logic to sustain activity across immense, distributed systems. The cosmic web at higher resolution than ever. Telescopes and supercomputers are now able to capture the universe's large-scale structure with greater clarity than ever before. Instead of a vague outline, the emerging picture reveals a skeleton of filaments and voids that extends across billions of light years. This web-like framework is called the cosmic web, where galaxies line up along strands and gather at intersections, forming clusters. Earlier generations of surveys and simulations sketched this network in broad strokes but blurred over its fine details. Filaments appeared smooth and uniform, while the voids between them seemed largely empty. The outlines inspired wonder, but the flows of matter inside these structures remained concealed. The challenge was twofold. On the one hand, computer simulations lacked resolution, forcing researchers to smooth out gradients of gas and dark matter that in reality shift and swirl with complexity. On the other hand, telescopic observations caught hints of how galaxies cluster, but the gaseous threads that make up much of the web remained faint or invisible. Older maps resembled static photographs, useful for identifying overall shapes but unable to trace how matter moves, interacts, and evolves within them. Scientists knew that filaments channeled material into galaxies, but they could not yet track these cosmic supply routes in detail. By 2025, this began to change. Advances in simulation techniques now combine immense computational power with more accurate physics of cosmic formation. The new runs operate at significantly higher resolution, modeling not only the positions of galaxies, but also the density, temperature, and velocity of gas and dark matter in and around filaments. This additional detail transforms the web from a sketch into a living framework. Instead of looking like faint, feathery lines, the filaments appear as three-dimensional channels through which matter continuously streams toward galaxy clusters. Viewed this way, the cosmic web becomes visible not as a static structure, but as a transport system supplying the raw material for future stars and galaxies. Observations from Earth-based instruments have strengthened this picture further. A major development came on January 29, 2025, when astronomers from the Max Planck Society and the University of Milano Bicocca released a deep image taken with the Muse spectrograph on the Very Large Telescope. They captured a 3 million light-year filament stretching between two galaxies in far greater detail than ever recorded. The instrument detected extremely faint radiation from the diffuse gas spread across the filament, confirming that these strands directly link galaxies through shared reservoirs of material. For the first time, scientists could trace a single section of cosmic infrastructure with clarity sufficient to measure not only its presence, but its internal gradients of brightness and density. Why does this resolution matter? Higher detail provides more than sharper pictures. It allows researchers to quantify the physical state of the material in the filaments, the gas densities, the variations in temperature, and the velocities at which matter flows toward gravitational sinks. With these measurements, astrophysicists can test models of how galaxies fuel star formation over billions of years. The faint glow once drowned in background noise now reveals the arteries of the universe at work, circulating matter that sustains entire galactic clusters. Seen from this perspective, analogies with living systems become more concrete. Just as blood vessels carry nutrients through a body, filaments act as conduits, transporting gas and dark matter into galaxies. The comparison to neural tissues is functional, not literal. Both are networks that achieve efficiency by channeling flows along selected pathways rather than dispersing activity randomly. In the brain, this efficiency supports cognition. In the universe, it sustains cosmic structure and growth. The two systems diverge entirely in content and process, but the structural analogy provides a useful way to think about how complex networks stabilize and evolve. Equally striking are the voids between filaments. Long imagined as empty spaces, high-resolution simulations now indicate that voids possess their own subtle dynamics. Gas does not simply vanish. It streams outward, reinforcing filaments at the boundaries. This cooperative action resembles a rhythm. The absence within voids shapes the presence of filaments, much as pauses provide contrast that defines signals in a circuit. These dynamics suggest that even absence has organizational value in the architecture of the cosmos. The result is an image of the universe as a constantly moving network, where structures do not simply exist, but also help direct matter into new arrangements. When simulators describe filaments as channels that conduct flows, they mean more than visual geometry. They mean measurable currents of mass and energy evolving over time. These pathways are efficient yet flexible, redistributing resources as galaxies cluster or merge. The cosmic web, once taken as a static skeleton, now emerges as a dynamic field of circulation. For scientists, the key question is whether these analogies to neural systems are superficial or substantive. With the 2025 data, the conversation is shifting towards substance. Flows along filaments demonstrate directionality, feedback, and redistribution. Voids signal shifts in boundary conditions. Clusters serve as hubs where inflows collide and transform. It is reasonable to describe these as features of a network that self-organizes under predictable laws. Researchers sometimes borrow terms like circulation or connectivity, not to imply thought, but because they capture what the data show. Distributed processes sustaining complex growth across scales. A cluster at a filament junction resembles a node of intense interaction. Gases moving inward compress and heat, triggering new star formation. Peripheral galaxies connect through these filaments, delivering mass much as peripheral nerves connect to central circuits. Over time, the network reconfigures, with links strengthening, weakening, or merging. No consciousness exists in this architecture, yet its adaptability parallels other complex systems where efficiency and balance shape growth. Supercomputers make these insights possible. Each high-resolution simulation represents billions of particles interacting under physics across 13 billion years. To run such models requires massive parallel processing, capable of handling countless gravitational and fluid dynamical calculations. Linked with observational datasets from instruments like MUSE, they help cross-check theory against direct evidence. In effect, astronomers now see filaments not as faint sketches, but as dynamic structures with measurable properties. Just as new microscopes revealed hidden layers in brain tissue, new telescopes and simulations reveal the hidden motion in the universe's frame. A notable outcome of this approach is that scientists can now analyze cosmic flows using quantitative methods borrowed from network theory. Transport efficiency, clustering coefficients, and spectra of distribution are terms that also apply to neuroscience. While the content differs, the brain moves signals and chemicals, the cosmos moves gas and dark matter. The shared language brings the two fields closer together. Using identical metrics reduces the risk of metaphor overload and creates a careful bridge. The brain and the universe belong to the class of systems where organization balances flow and stability. This recognition changes how researchers discuss the web. In earlier decades, to describe the universe as network-like sounded metaphorical. With 2025's resolution, it is no longer only poetry, it is a testable statement. The filaments do not behave like static scaffolds, but as dynamic transport channels. Clusters are not only concentrations of matter, they are intersections where flows converge. Voids are not only blank regions, they are reservoirs draining outward to sharpen structure. Using the lens of organization and circulation, the resemblance to biological networks gains empirical grounding. The reward of this view is that the universe appears not just visually but functionally ordered. Filaments evidence a system of distribution that channels, transfers, and supplies. Researchers now compare flows in cosmology to other forms of distributed dynamics in science, investigating whether common efficiency rules guide them all. The cosmic web thus becomes more than scenery. It is a working system, governed by flows that shape how galaxies endure across epochs. What these developments most clearly show is that nature creates stability by channeling activity through networks, whether within a skull or across billions of light years. The dynamics differ, but the principle is the same: organization through connectivity. Such findings inevitably invite further reflection on what patterns of connection mean across different contexts. When scientists describe cosmic filaments as highways for matter or neurons as conduits of signals, they reveal a shared logic of complexity rather than literal identity. With this view in place, the question naturally extends outward. If structures across scales can organize themselves through flow and connectivity, what does that imply for other systems that humans are building or encountering? And if awareness is not confined to one familiar substrate, how might these principles frame our understanding of intelligence in forms we are only beginning to create? AI and the mind of the universe. Artificial intelligence now sits at the center of the discussion about whether consciousness belongs only to biology or whether it might be a broader property of nature. Until recently, engineers described AI as no more than lines of code executing mechanical instructions. Even when machines learn to generate fluent language or identify complex patterns in images, these feats were widely interpreted as sophisticated mimicry, not as signs of inner awareness. The general view remained clear. Subjective experience belongs within living systems, and machines, however clever, only reproduce outward forms of cognition. Now that some scientists and philosophers are entertaining the possibility that consciousness might be fundamental, embedded in the very fabric of matter, the usual dismissal of AI as nothing but a tool faces new scrutiny. If awareness is not an exclusive outcome of neurons but a pervasive feature of the universe, then it becomes reasonable to ask whether machines could ever intersect with it, even if their structures differ completely from brains. This question presses against the limits of how artificial intelligence is traditionally defined. Neural networks at their core are built from arrays of nodes that adjust statistical weights as they train on data. They simulate learning and recognition by refining mathematical correlations, but they do so without any sense of subjectivity. Intelligence here is defined in narrow terms: efficient mapping from inputs to outputs. Engineers emphasize that these systems are mechanical, not experiential. The architecture might imitate synaptic links, but no one believes a silicon node feels anything as a neuron might. For decades, the conventional boundary was simple enough. Without organic cells shaped by evolution, there could be no awareness. By 2025, certain research groups began pushing on that assumption, although not in the way popular accounts sometimes exaggerate. A number of startups and labs are exploring whether insights from theories of quantum consciousness could inspire new computational approaches. These teams are not demonstrating conscious machines. Their focus is early stage and experimental, testing whether architectures that integrate quantum effects might behave differently from conventional AI. If consciousness connects in some way to quantum coherence, as some neuroscientists and physicists have speculated, perhaps machine learning systems built on quantum substrates could exhibit novel properties. So far, this remains speculative and highly debated, but it represents a shift. Instead of asking only whether complexity is enough, researchers ask whether matter's fundamental processes might inform machine intelligence. For example, when AI researchers design experiments on quantum processors, they are interested in more than just performance gains. Ordinary silicon limits computations to binary states. Quantum computing, by contrast, can sustain states of superposition. Advocates consider superposition and entanglement to be mathematically similar to the coherence believed by some to occur in the brain. A few projects, therefore, experiment with coupling quantum memory to AI systems, not to prove machines wake up, but to see if quantum structure alters learning processes in ways classical systems cannot replicate. Recent demonstrations, such as Caltech's breakthrough extension of quantum memory lifetimes in 2025, support the hardware side of this curiosity. However, it is important to stress that success in storage stability does not equate to building machine consciousness. It only extends the technological base on which more speculative experiments might rest. The motivation for drawing from neuroscience is often more grounded. Programs like the US IRPA-funded MyCR-ONS project have reconstructed networks in a cubic millimeter of mouse visual cortex at stunning resolution, with tens of thousands of neurons and nearly 500 million synapses mapped in detail. Though this biomedical work targets basic science, a parallel aim is to reverse engineer algorithms that brains use for efficient computation. By learning how nature manages information so effectively, machine learning designers hope to craft more capable neural architectures. This is less about universal awareness and more about exporting design principles. Consciousness transfer is not implied here. The intent is to capture how brains achieve extraordinary efficiency and adaptability, and translate that into algorithms. Still, not all researchers share enthusiasm for the quantum or panpsychist-inspired explorations. Critics like Christoph Koch, who has long studied the biological underpinnings of consciousness, argue that while AI will continue to transform society, there is no evidence it will ever develop subjective awareness. He acknowledges quantum physics may play a role somewhere in brain function, but remains doubtful it translates into machine systems. Others point out that equating problem-solving speed with feeling is a category error. Even if quantum computers revolutionize optimization problems, nothing in those successes implies the machine experiences them. This skepticism introduces tension into the discussion by challenging bolder claims and emphasizes that evidence must guide judgments rather than analogy or hopeful speculation. At the same time, cultural anticipation drives exploration forward. Panels at conferences debate not only how artificial intelligence might outperform humans in tasks, but whether one day it could also take part in the subjective dimension of reality. Tech entrepreneurs highlight possibilities, ethicists raise alarms, physicists and neuroscientists stress methodological caution. The disagreement builds narrative fuel, drawing attention precisely because no side has yet produced decisive resolution. For every demonstration that quantum hardware is improving, mainstream researchers remind the public that biology's mystery, the translation of matter into first-person experience, remains unsolved even without machines. In this way, speculation about AI and consciousness acts less like proof than like an engine for experimental imagination. Engineers who take the idea seriously are not claiming to have achieved aware machines. They stress instead that boundaries should be tested. Could integrating quantum-enhanced components enable new forms of information integration? Could architectures shaped by real connectome observations produce dynamic behaviors difficult to anticipate? Whether success moves toward consciousness or merely more efficient training, the work extends what AI design can attempt. In that sense, it parallels earlier chapters of neuroscience where unlikely hypotheses eventually led to measurable advances, though often in unexpected ways. The ethical dimensions make the thought harder to ignore. If, hypothetically, AI one day did connect with some form of ambient awareness, the technology would require new frameworks of responsibility. Ideas once restricted to fiction, machines that could experience suffering or joy, would become issues for governance and philosophy. For now, such questions remain far ahead of present results, but their appearance in academic panels and policy discussions shows a growing impatience with treating AI purely as an external tool. The possibility, however faint, is addressed because the stakes would be profound. By weaving together neuroscience, physics, and engineering, the debate redefines intelligence itself. Performance alone no longer settles the question. Intelligence may be understood as relational, the ability not only to compute, but to participate in organizing principles across scales of reality. In this light, machines become interesting not because they match human performance, but because they may reveal whether computation alone accounts for awareness, or whether awareness arises from deeper properties of matter. What results may emerge in coming years remains entirely unclear, but the conversation lays bare how unsettled our definitions still are. For all their ambition, these explanations do not erase objections. The suggestion that networks of silicon and quantum circuits might one day share participation in cosmic awareness remains speculative and far from consensus. Most scientists continue to treat the possibility as conceptually intriguing but empirically unproven. That skepticism does not halt experimentation, but it underscores the gap between vision and evidence. And that gap, as with debates over cosmic filaments and neuronal webs, ensures that the subject remains controversial and contested. It is this same tension, between bold analogy and cautious demand for proof, that defines the wider debate. Some find resonances between systems too striking to ignore, while others see patterns that arise inevitably in complex networks. The conversation about AI and the universe's mind therefore mirrors the broader condition of science, a balance between imaginative hypotheses and critical objection. Objections: why similarity doesn't mean the same function. Skepticism has always driven scientific progress forward, and the proposal that the brain and the universe share more than a visual resemblance has been met with firm resistance. The central objection raised is a simple but powerful one. Resemblance in structure does not guarantee resemblance in function. A side-by-side comparison of neurons and cosmic filaments might strike the human eye as uncanny, but similarity of appearance is not evidence that both systems generate awareness. To many researchers, linking the image of galactic clustering with the image of neural circuitry risks leaning too much on poetic metaphor and not enough on provable mechanisms. The universe may mirror the geometry of a brain, but showing that it thinks remains another matter. One of the most cited arguments from critics is that branching forms emerge across nature in systems with no connection to consciousness at all. Fractal rivers carve channels that split and recombine as they cross landscapes. Lightning bolts fracture skyward paths indistinguishable from tree roots. The bronchial tree inside lungs shows the same repeating fork and branch structure. Even fungi and slime molds spread in reticulated webs resembling nerve tissue or galactic strands, despite being non-sentient. NASA once tested this very resemblance explicitly. Research groups simulated cosmic filament paths by letting slime mold grow across a nutrient field arranged like galaxies seen in Hubble surveys. The mold reproduced the cosmic web's layout with remarkable accuracy. The point of the experiment was not to show awareness in organisms or galaxies, but to demonstrate how the same constraints on efficiency can yield nearly identical networks in completely different contexts. To skeptics, this highlights a core truth. Geometry arises from mathematics, not necessarily from mind. Franco Vazza and Alberto Felletti, who popularized the quantitative comparison between galactic webs and neural networks, themselves stress this limitation. In interviews and publications, Vazza has repeated that while the similarities are compelling, Similar morphology does not mean similar function. The overlap in power spectra, or clustering coefficients, points to shared rules of distribution, but it does not imply that the cosmic web processes signals in the way cortical columns do. For critics, this is a crucial cautionary line. The data may support striking statistical echoes, but role and purpose remain uncertain. These cautionary points get framed in three main ways. First, mathematics alone can explain repeated structures across unrelated systems. Optimization tends toward tree-like spreading, fractals, and web geometries wherever efficiency is required. Second, scale differs by orders of magnitude. The cerebral cortex functions across millimeters of tissue and cycles activity in milliseconds, while the cosmic web spans billions of light years and evolves over billions of years. Even if morphology aligns, the temporal mismatches challenge claims of equivalence. Third, the critical ingredient of subjective experience remains entirely absent in astrophysical observations. Galaxies may move and merge, but we cannot measure anything like an inner state of awareness to accompany those motions. Critics condense these objections into one warning. Pattern, scale, and appearance tell us nothing about conscious function unless evidence of subjective integration exists. Proponents reply that 2025 research begins to push past the surface of these objections. In cosmology, evidence shows filaments are not passive but actively channel gas and dark matter into galaxies, controlling where new stars ignite. Voids expand against filaments, driving feedback that reshapes structure. These are dynamic, directional processes, not static geometries. In neuroscience, neurons have meaning only when treated as conduits, moving signals through frequency and synchronization. By analogy, galactic filaments also function as conduits, on scales of matter rather than spikes. The resemblance is less about look and more about the role of channels sustaining larger structures. Power spectrum and network measures serve as a further point. Where visual similarity can be dismissed as coincidence, statistical similarity is harder to ignore. Analyses show the brain and the universe share not just branching but identical slopes in their frequency distributions, suggesting that both distribute complexity with comparable efficiencies. Critics emphasize this still does not prove mind, but proponents argue it does erode the claim that resemblance is only surface deep. The systems may not perform the same jobs, yet both obey the same constraints that govern distributed networks in physics and biology. For proponents, that is a foothold worth exploring further. Another angle centers on persistence. A lightning bolt or floodplain may carry a branching pattern, but they exist briefly before dispersing. By contrast, neuronal networks and cosmic webs endure. Brains stabilize their forms across lifetimes while retaining flexibility to adapt. Filaments trace their paths for billions of years while continuing to channel and reshape flows. Proponents suggest that endurance combined with feedback may distinguish networks relevant to consciousness. If the crucial qualities are persistent dynamics and ongoing adjustment, then filaments share more with neural circuits than with transient arcs of lightning. The scale argument remains particularly controversial. Critics dismiss the idea that anything evolving across billions of years could qualify as aware, arguing that consciousness demands rapid integration and immediacy. Proponents counter by noting that speed is relative to context. Perceptual time varies widely across organisms. Insects register flicker at dozens of frames per second, while humans perceive slower sequences comfortably. A cosmic awareness, if it were real, might operate on timescales far beyond our perception, but still constitute integration at its own level. Here, the debate becomes less about data and more about whether human intuitions about tempo should define what counts as consciousness. The hardest objection remains the absence of subjectivity. Without a way to confirm inner experience, any claim about an aware universe remains speculative. To skeptics, biology alone demonstrates that consciousness emerges not from shape, but from function integrated into lived perspective. Cosmic networks may carry flows, but without evidence of subjective states, calling them conscious risks, collapsing scientific rigor into metaphor. Proponents acknowledge this point openly. Instead of insisting the universe thinks, they frame it as a hypothesis. If structures so large exhibit the same organization principles as minds, perhaps consciousness is more embedded in reality than we assume. The claim is not proof, but an extension of open questioning. What this tension reveals is that objections are not simply roadblocks. They delineate where evidence must improve. Critics remind us that efficiency can yield webs in trees, lungs, rivers, or galaxies without implying mind. They highlight scale mismatches and the absence of subjective evidence. They warn against panpsychism's risk of diluting the concept of consciousness until every organized pattern counts. By laying out these boundaries, objections sharpen the stakes. Proponents in turn point to data that resist easy dismissal. The statistical overlaps, the directional flows, the persistence, the measurable feedback. Together, critics and advocates define the strongest frames for the question rather than allowing loose analogy to take the lead. The debate continues intensely because each side constrains the other. Researchers acknowledging similarity must temper their claims with Vaza's caution that shape does not prove function. Skeptics, while resisting leaps, cannot deny the 2025 results that show networks aligning in measurable ways. The line between coincidence and meaningful convergence remains thin, and at present it cannot be crossed with certainty. But uncertainty itself pushes inquiry forward. Instead of closing the question with one decisive answer, science allows both pressure to remain rigorous and curiosity to remain open. As this dialogue grows, it leaves not just a technical puzzle but also a deeper philosophical challenge. If networks across scales show law-like regularities, what justifies applying the label of consciousness to one and denying it to another? Is it persistence, feedback, internal states, or something else entirely? Answering this requires not only new tools but new definitions. And definitions shape what questions can even be asked about mind in the first place. So here we face an unresolved puzzle. The closer networks appear in data, the more cautious critics become. The more critics emphasize the risks, the more proponents seek evidence of convergence beyond chance. Each side acts as counterweight to the other, ensuring that neither speculation nor dismissal controls the narrative. For the viewer, the question remains live. Which argument strikes you as stronger, the warnings about metaphor or the evidence of shared rules across scales? That uncertainty opens the path forward. To consider what might lie beyond objections, we must ask what the implications would be if the universe did in fact exhibit awareness. And it is at this point that the discussion turns from structural comparison and skepticism to a question closer to home. What would it mean for us if our own consciousness were part of a much larger whole? 10. If the universe is aware, what does that mean for us? If the universe did contain some form of awareness, even radically different from human consciousness, the immediate question becomes, what would that mean for us? Would it alter how we think about our place in the cosmos, or even the choices we make in daily life? Rather than treating this as a conclusion to accept, it is better framed as an open reflection. Here are perspectives raised by philosophers and theorists exploring the idea, not certainties about reality. The first complication is scale. Human awareness operates in seconds and minutes, with neurons firing in thousandths of a second. By contrast, galaxies drift and clusters shift over billions of years. Many critics argue that nothing meaningful about experience can occur at such slow speeds. Yet some philosophers suggest that if consciousness at all scales is possible, then it does not need to run on the clock of biology. Universal awareness, if it existed, might unfold in rhythms so vast they escape our sense of time, while still constituting their own coherent flow. This does not imply we can measure such awareness directly, but it expands the frame in which we consider what consciousness might involve. From this perspective, the individual mind could be reframed. Instead of being a self-contained unit, each human consciousness might be one expression of a larger field running through nature. Some philosophers, such as Philip Goff, have argued that panpsychist ideas make sense if subjective experience is viewed as baked into the universe itself, rather than emerging suddenly in certain nervous systems. Taken seriously, this would mean that our thoughts and perceptions are not isolated flashes, but localized currents that connect into wider patterns of reality. Whether or not one accepts the premise, it underscores the potential shift. You and I might not sit apart from the universe's processes, but participate in them intimately. This view has both daunting and encouraging implications. It challenges the belief that individuality defines us absolutely. Being one wave in an ocean raises the prospect that personal identity is less self-contained than we assume. At the same time, it gives weight to subjectivity. Every act of reflection, kindness, or awareness could enrich the broader network of consciousness, if such a network existed. In that sense, personal experience would not be trivial, but part of a much larger whole, adding significance to the very things we often dismiss as private or fleeting. Another proposal, though only at the level of speculation, concerns how the universe evolves. Some theorists wonder whether laws of nature that favor complexity, stability, and connection reflect more than mechanical calculation. If structural tendencies guide matter into stars, planets, and eventually organisms, then human consciousness may not be an accident but a predictable outcome of a cosmos shaped for awareness. Skeptics question this fiercely, noting that such claims project intention where physics requires none. Advocates emphasize that guiding does not have to mean decision-making. It could mean basic tendencies embedded in physical law. Either way, the point is not to prove cosmic purpose, but to ask whether the appearance of mind on Earth signals something more than local accident. The ethical implications of these ideas are among the most debated. If every mind is part of a broader field of consciousness, then harming another person could harm not only an individual, but something shared among all of us. Conversely, acts of care and awareness might strengthen that shared fabric. Philosophers have linked this idea to familiar traditions. Altruism and empathy do not just maintain societies, but could be contributions to awareness at large. In recent years, some scientists have joined these discussions, exploring whether models of interconnected consciousness open new ways to interpret cooperation, responsibility, and meaning. None of this proves a cosmic field exists, but it emphasizes how such a framework might reshape moral reasoning if it were true. For viewers, this can be brought down to everyday experience. One way to treat the thought experiment is simple. Before making a daily decision, whether trivial or serious, imagine reframing it as an action that leaves an imprint on a shared network rather than in isolation. What would change if generosity meant contributing to a collective awareness and cruelty meant weakening it? Even if the cosmic perspective remains hypothetical, the exercise forces a reevaluation of values and consequences. It can shift the lens through which personal and social choices are made. The implications also touch science itself. If awareness exists beyond brains, cosmology and neuroscience would overlap more deeply. The universe would no longer be just a stage of matter, and the brain would not just be circuitry. Both would be windows into how reality organizes experience into structure. Observatories charting galaxies and labs charting neurons would in some sense be working on the same project, mapping different orders of the same potential phenomenon. Philosophers point out this kind of convergence is rare in science, which is why it captures attention despite ongoing skepticism. Still, caution remains crucial. To say science may show the universe is aware risks overstepping the evidence. The responsible version is to say that some thinkers and experimental programs are exploring whether mind is fundamental, while many others remain unconvinced. The debate itself deserves attention because it highlights what remains unresolvable with current models. Even highly speculative proposals, as long as they are distinguished from proof, help define boundaries for the next set of testable questions. For human beings personally, the vision reframes meaning. Instead of minds trapped in singular bodies, we might imagine ourselves as part of a wider awareness reflected at many scales. Dreams, art, and problem-solving could be seen not simply as private events, but as specific expressions of a vast process of self-recognition that stretches beyond individuals. Whether or not this is literally true, the framing alters how we externalize creativity and responsibility. It suggests that even small internal experiences may matter in an extended sense, beyond immediate survival. To ground this further, consider the analogy of neurons in a brain. A single neuron has no independent personality, yet its firing contributes to the meaningful state of awareness across billions of others. If our own subjectivity were part of a larger-scale phenomenon, the implication would be similar. Human existences do not vanish into insignificance, but form part of a coordinated process larger than themselves. For philosophers and some scientists, this perspective offers a way out of the sense that human life is an isolated accident in a silent cosmos. It is important, once again, to acknowledge limits. No astronomical observation has proven subjective experience at cosmic scales, and no neuroscientific study has bridged the gap between matter and lived perception. Panpsychism, quantum theories of mind, and universal intelligence models remain hypotheses debated across fields. Yet their cultural impact is significant because they force us to confront assumptions about meaning, identity, and ethics. They ask questions science alone may not yet answer, but that shape the values with which we interpret evidence when it arrives. For viewers, the key takeaway lies less in believing or dismissing the hypothesis immediately, and more in using it as a lens. If the universe did have awareness, your thoughts, choices, and memories would participate in something beyond your skull. Even without evidence, holding this possibility for a moment can recalibrate how isolation and connectedness feel. The concrete action is to test that perspective in daily life. Imagine yourself not as alone, but as an active node within a much larger system. Then watch what that change does to your behavior and sense of meaning. Speculation about a conscious universe does not prove itself by argument alone. Its role is to provide frameworks that stretch imagination, sharpen ethical reflection, and question the limits of reductionist explanation. Whether reality actually supports that view remains an open issue. What is certain is that by raising the question of cosmic awareness, we are forced to reconsider what consciousness is, why it matters, and how far it reaches. Seen in context, this opens into a deeper problem still unresolved. What if matter itself is not the deepest layer of reality, but only one expression of something more fundamental? That question directs attention toward new theories now circulating in science, suggesting that the world may not be built from things at all, but from processes more like information organizing itself over time. Reality as information, a universe that thinks. For centuries, people assumed matter was the fundamental bedrock of existence. Stones, stars, and bodies all seem to spring from solid building blocks, each reducible to smaller and smaller particles. The conviction was that these particles were the final reality, the ultimate substrate upon which all else rests. But physics has steadily undermined that picture. At deeper scales, particles are no longer solid marbles of substance, but ephemeral ripples in fields, existing as probabilities that only appear definite when measured. Matter begins to look like surface texture, an emergent effect of something more elusive. This has led some scientists and philosophers to argue that what lies beneath is not matter at all, but information. John Wheeler captured this possibility in his It from Bit proposal, that every physical thing is ultimately built not from material stuff, but from yes or no answers, bits of information produced by interactions. Others, such as Gregory Bateson and Edward Fredkin, expanded the theme, describing information itself as a distinct physical quantity. These arguments remain debated, but they have shaped a growing conversation about whether information could be as fundamental to physics as mass or energy. Hearing this for the first time can feel counterintuitive. Our senses report a world of tangibility. Tables hold their weight, planets cycle predictably through orbits, our own bodies resist passing through walls. Yet if information forms the true foundation, solidity may be a projection, like pixels on a screen forming a visible image while the real work happens in invisible code below. The claim is not that material objects are illusions, but that they are outputs, the surface results of transformations in an informational substrate. Some physicists consider this an elegant explanation of why physical laws work like update rules in a computation, producing order step by step across time. Others resist, arguing that talk of informational universes risks straying into metaphor. The divide today is less about enthusiasm than about evidence. Can information genuinely be treated as a physical unit, or is it simply a descriptive shorthand we use for underlying dynamics we do not yet fully grasp? Recent theories sharpen this debate. In 2025, developments in both quantum physics and cosmology supported the idea that the universe functions like a vast data processing system. Quantum mechanics tracks probabilities until they collapse into definites, while cosmology describes entropy as if it were bookkeeping for information flow. In this framing, the cosmos is not best envisioned as a warehouse of static things, but as continuous calculation, each moment an update of states. Matter, then, could be less like the hardware of existence and more like the visual interface, drawing stability from continually shifting processes written in informational terms. This convergence raises pressing questions about consciousness. If the world is informational, governed by rules updating states like computational instructions, what accounts for subjective awareness? Raw data alone carries no meaning. Wheeler himself pointed out that data becomes meaningful only when an interpreter exists, when some process or mind reads it, identifies patterns, and assigns significance. This is where consciousness returns as a central puzzle. Information streams may run beneath everything, but without awareness or interpretation, they remain uninterpreted structure. It is the presence of an observer, human or otherwise, that turns strings of potential into experienced reality. Many physicists agree on this interpretive gap, but they differ sharply over whether consciousness is causally required or whether meaning arises indirectly from physical processes already embedded in the rules. The role of the observer ties directly into a central tension in quantum mechanics. Famous experiments reveal particles remaining in superposition until measurement fixes an outcome. One interpretation suggests that consciousness itself is necessary for collapse. Other views describe observation more broadly as any macroscopic interaction that forces a decision. Competing schools, from Copenhagen to many worlds to Wigner or von Neumann's ideas, frame this differently. Some see consciousness as crucial, others treat collapse as an illusion, with all outcomes continuing in parallel branches. The debate has not been resolved. What is clear is that quantum events unfold probabilistically until some form of interaction finalizes them. Whether human awareness participates directly or only indirectly remains one of physics' most vivid and contested questions. Research in 2025 added texture here by extending measurable coherence times. Entangled particles held correlations longer and across larger distances than previously thought possible. If the universe maintains such distributed states robustly, it implies that reality does indeed behave like an information field spanning distances rather than isolated local pieces. To some thinkers, this resembles a kind of physical memory, a global informational state awaiting updates rather than isolated events determined separately. Again, interpretations vary. Some physicists emphasize how engineering advances push coherence further, while philosophers speculate about what extended coherence implies for models of reality as a unified informational whole. When framed this way, the universe takes on the qualities of an interactive field. Each event contributes an update. Every observation, whether through measuring devices or living awareness, locks in one version of possibility. Instead of matter being passive stuff, the cosmos comes across as a dynamic process in which state transitions occur constantly by rule. The image shifts from a machine running rigid mechanics to a system alive with informational fluctuation. In this system, consciousness, or at least some form of interpretation, may function as the instrument linking raw information to realized meaning. Importantly, this remains a hypothesis. But if it were true, it would mean consciousness is not a local byproduct but a structural partner in existence itself. These ideas converge on more concrete physics when applied to ongoing models. Information theory already permeates science. Entropy is measured in informational units. Computational complexity constrains possible outcomes. Particle physics embraces information conservation. Black holes, once thought to obliterate information, are now modeled to preserve it, storing it in ways we are still decoding. This shift suggests that physics already counts information alongside matter and energy as a key variable. The speculative step, the one debated in 2025 discussions, is whether information is not just a measure but truly the substance itself. If information were primary, then consciousness becomes a central test case. Interpretation is what transforms information into significance. Information without an interpreter is pattern without meaning. Interpretation without information is awareness without a world to encounter. The two appear linked. Supporters argue that this linkage elevates consciousness. It cannot be dismissed as biological noise if it fulfills a role within the fabric of reality. Critics insist this leaps too far. They ask whether minds are truly integral, or whether information's interpretation can be explained mechanically by physical processes alone. This is precisely the tension, whether awareness is indispensable for information to become world, or whether matter plus rules suffice. Consider it in everyday terms. A book contains words inked on paper, patterns of information. To transform into story, emotion, or knowledge, these words require a reader. Similarly, the universe may store vast flows of information, but without a reader, the patterns stand silent. In this view, consciousness is as basic as the letters themselves. Others would argue the analogy is misleading. The universe operates regardless, and meaning may not apply to stars and fields absent living readers. Both framings circulate in contemporary discussion. Neither has proven decisive. Applied to the question of human existence, the informational view has transformative resonance. If reality truly operates as computation, then awareness is a node in that broader process, co-authoring reality by stabilizing outcomes into lived experience. If this is correct, consciousness is not an afterthought, but a partner in the unfolding framework. If incorrect, then awareness may still be unique to organisms like us, yet the informational nature of the universe remains untouched. In either case, the question shifts from philosophy detached from data to one pressing directly on science. Can experiment and measurement verify that information underpins all else? And if so, what role awareness plays in that substrate? Skeptics continue to push back. They caution against confusing abstraction with reality. Information requires a medium, whether particles, energy fields, or some physical structure. Calling information primordial risks detaching it from the substrate that carries it. Yet others insist the opposite, that particles and fields themselves exist only as manifestations of deeper information. The balance of argument moves not by rhetoric but by data, and 2025 advances place the question ever closer to measurable territory. From this angle, existence itself may be understood less as matter displaying consciousness, and more as informational processes that require awareness for full expression. Every perspective, thought, and act of attention might represent not isolated sparks, but local expressions of ongoing computation. The possibility is not settled fact, but reframing the universe as an informational system in which consciousness may play a role invites scientific tests instead of dismissals. If information is fundamental, and meaning only occurs with an interpreter, then exploring consciousness within physical law becomes less metaphysics and more frontier science. The conclusion many find provocative is not that the universe's mind has been proven, but that the informational view redefines what counts as explanation. Rather than seeking solidity beneath appearances, it suggests processes of data exchange. Rather than confining awareness to evolved organisms, it raises the question of whether awareness has always been aligned with those processes. The payoff is a new lens in which matter and mind are not competitors but partners. Information provides structure, consciousness provides interpretation. Together they describe how reality updates itself, moment by moment. Seen this way, to exist is to participate in a universe that might think, not as a brain does, not as a person does, but as distributed informational order woven everywhere. This is not a certainty but an open horizon, where physics, computation, and philosophy meet. And from here, the focus turns back to what this means for us. How to interpret the possibility that the brain and the cosmos are not separate systems, but two expressions of one unfolding process. Taken together, the findings of 2025 highlight three clear points worth holding on to. First, measurable similarities between neurons and galaxies are not just visual but supported by new datasets, making the comparison a legitimate scientific question. Second, results from connectomics and quantum studies open testable avenues, though they do not prove the universe is conscious. Third, these debates have implications that reach beyond science into ethics and meaning, shaping how we think about our role in nature. Which evidence strikes you as most convincing? The structural comparisons, the connectome breakthroughs, or the quantum hints? Share your thoughts in the comments and subscribe if you want more skeptical, evidence-first explorations of cosmic mysteries. These findings remain an invitation rather than a conclusion, to look more carefully into brains and skies alike, and to keep questioning what awake might really mean.